Okay, this is Laurent's multiplier video. So yeah, so basically what I talked about before was how the gradient vector, right, is the steepest, fastest way up a curve, right? So if I have this, let's remove some of the bounds, right? So I'm gonna consider only the first octane. So I have this, right? And I have this, and I like this, and this, and a circle, and it goes up like that, right? And that's kind of a bowl, right? So this is gonna be like some value z equals negative x squared plus y squared. Is it? Wait, is that the equation? Z, no, yeah, it's then plus 4. Okay, so that's gonna be like the equation, right? So this is gonna be 4. Okay, so so let's draw some contours onto this sheet, right? And then my gradient vector is going to point the path for steepest, right? So it's just always going to be perpendicular to the contours. We talked about this, right? So it's going to be like that, like that, okay? And yeah, okay, that's the basic concept. So Laurent's multiplier. So let's say I have another disk, right? Like a plane, right? So if I have a plane that goes from here, we'll cut this off, right? And so the box is probably the easiest one, right? I have that box, and I have that box, right? And I want to find the multiplier for this. First of all, it's just really ugly, so yeah. So conceptually, what's happening here? So I'm gonna only look at this one, so this box, right? The yellow box. Okay, so this yellow box. Okay, so look the box like this. Okay, and then this is gonna be the z. Okay, I put this, and this is gonna be y. Okay, and from my view on the box, right? So I'm gonna cut this box, right? Like I'm gonna cut the surface, right? So this is gonna be the surface of the the surface of the curve, right? Because this is like a curve onto the plane I drew, right? So I don't know, something like that. Okay, and now I want to draw contours, right? So from here, right, my contours are look like that, like that, like that, right? Okay, so from here, my contours for, so now I'm going to draw the gradients for this function, right? This yellow one, this yellow function, I'm going to call equal to g. This yellow function is going to be equal to g of x. Okay, so what I do is, so I'm going to draw my gradients for, what is it? My gradients for my function g of x, right? Because g of x is going to be the plane, the restriction onto the curve. So here's that. Okay, and I'm going to call these all g prime of x. Okay, and now I have to draw the gradient vectors of all of my contours that I intersected, right? So it's going to be like a straight line. Right? Okay, and my contours are going to be like that. And hopefully you can see what happened. So basically what Laurent's multiplier is, right, is that I want to find the place where it's steepest for both the g of x, right, because g of x is a restriction, right, so g of x, at position g of x, is going to be the function f of x is going to be increasing the fastest. So what happens is that so that only occurs when this is parallel, right, so the gradient of g of x is parallel to the gradient of f of x, the gradient of f of x. And so you can see what's happening here. Like I'm right here, right, on this side of the circle. Like so, right, let's say I take a point here. If I'm right here, right, I'm only growing like that, right? That's not really a max, right? So the max is when this is only parallel to that, because when the shape like this happens, right? When the normal vector is pointing straight upwards, you know what that means, right? That means it's a max, right? Because that's going to be the normal vector. If I draw a plane here, right, it's going to be 0. So that's how I know it's going to be a max. So that basically is what's happening here. And so basically, this vector is going to be parallel, like this vector is going to be parallel to that vector, okay? And it's not going to be the exact same vector, because g of x is a different function of f of x, right? So it's going to vary by a multiplier, and this multiplier is lambda. So we know a max occurs when lambda g of x is equal to lambda f of x, and that's Lagrange's multiplier. And then so when you're solving these kind of problems, right, you just kind of plug and chug, right? You find the directional derivative of f of x. Okay, it's supposed to be two variables, so x of y, my bad. It's two variables, right? So I take each component of x separately, so I get like f and then g of x, right? The first derivative with respect to x is equal to f with respect to x. And lambda is g of y equals f of y. And I have an equation. I have two variables, two unknowns, and an x value here, and yeah. And you solve the system equation. No, you have two variables, two equations, and you solve the system. And then once you solve the system, right, you'll get values x, y. You'll get some value x, y's. I don't know how many you'll get, right? It depends on the problem, right? And then you plug it into the original equation f of x. And that's how you solve it.